We begin taking a look at Chapter 2 by talking about inductive reasoning. Now, before we get into what inductive reasoning is and its definition, we're going to take a look at a couple examples here. In the example that we have listed, A through D, what we want to do is we want to find out what is the next term going to be in each of the patterns that are listed. So I'm going to run through A with you, and then we'll have you do B through D on your own. So the first one, A. It looks to me as though we've got months listed, and using my prior knowledge, I know that every year starts off in January, and I know, however, the next month that comes after January is definitely not March. It's February. So it goes January, February, and then March. So it seems to me as though we skipped a month. Then I know from March, it goes on April, and then May. So it seems to me, again, as though we've skipped another month. So it looks to me like the pattern is I have a month, and then we skip a month. So January, then the February was skipped, then we have March, and then the April was skipped. So we have May, meaning the next term I should have isn't going to be June because June has to be the one that's skipped. So the next month should be July. If you continue the pattern on, it would be August is skipped, and then September would be the next one. However, it only just asked for the next term, so I'll leave it as is. How about you go ahead and try out B through D on your own? Pause the video, and when you're set, start it up again, and hopefully we have the same answers. So let's go ahead and take a look at the answers. For B, I ended up getting the next term as 35. I noticed that the pattern that we had started off at 7, and then it went to 14, which was a difference of 7 units, and then the next one was also a difference of 7. So it almost looked like I was adding 7 to each term to get the next one. So if I add 7 to 28, we get 35. In part C, I looked at how the triangle was being rotated, and I noticed it started on almost like the vertex was pointing up, and it rotated counterclockwise. So if I rotate the last term, or the last triangle, counterclockwise, I'd end up getting a triangle pointing actually off to the right-hand side. And in part D, we started off with 4/10, and it almost looked like I added a 0 in there, but what really it is it's being multiplied then by 1/10. So I have 4/10, so then 4/100ths, and then 4/1000ths, so the next term would be 4/10,000ths. So the previous example kind of led us into what inductive reasoning is. Inductive reasoning is the process of reasoning that a rule or a statement is true because we know that specific cases are true. So how does this play a role when we talk about a conjecture? Well, a conjecture, which we're going to work a lot with in this chapter, is a statement that you believe to be true based on what you've used through inductive reasoning. And if you want to show that a conjecture is indeed true, all you have to do is just prove it. However, if you want to show that a conjecture is false, all you have to do there is just find one example where it is not true. And that'll lead us to what a counterexample is later on in the notes. So for the following example, what I want to do is I want to complete each conjecture, meaning I want to use my inductive reasoning to figure out what do I need to put in the blank to make this statement true. So I'm going to go through A, and then you're going to try B and C on your own. So A, the sum of two positive numbers is, well, let's think about that. If I'm talking about two positive numbers, it can be any two numbers that I want. Maybe 3 and 7. The sum, meaning the addition of them, well, in this case, I'd end up getting 10. Okay, well, that's great. What if I ended up picking 24 and 11? Well, I'd get 35. So it's not going to be that I'm getting an even number or an odd number, but I do notice that every time I add two positive numbers together, I'm always getting a positive number out. Therefore, to complete my conjecture, I would say that the sum of two positive numbers is positive. And I really cannot think of any possible way in which this conjecture would be false. So that's what we're going to do for A. Once you go ahead and try B and C, pause the video, and when you're set and ready, go ahead and start it up again. So let's go ahead and take a look at part B together. The number of lines formed by 4 points, no 3 of which are collinear, I ended up getting was 6. So if I were to draw out 4 points, and making sure that 3 of those, no matter which 3 I chose, were not on the same line, I'd end up getting something like this. And if I were to draw in my lines that would connect them, how many lines could I get? Well, I've got 1, I've got 2, I've got 3, I've got 4, and then don't forget you can put 5 and 6. So no matter how hard you try, when you plot out 4 points and make sure that no 3 of them are collinear, you're always going to end up getting 6 lines. So hopefully you ended up getting that for B. In C, the product of 2 odd numbers is odd. If I take 3 times 3, I end up getting an odd number. What if I took 5 times 1? It's odd again. Or 7 times 9, we get 63. I'm noticing the pattern there where I'm always ending up getting an odd value out when I took the product of 2 odd numbers. So in this example, we're going to take a look at 2 different types of whales. And it says, the cloud of water leaving a whale's blowhole when it exhales is called its blow. A biologist observed blue whale blows of 25 feet, 29 feet, 27 feet, and 24 feet. Another biologist recorded humpback whale blows of 8 feet, 7 feet, 8 feet, and 9 feet. And what we're going to do is, using the chart that we have here, we're going to go ahead and make a conjecture. So what I want you to do is I want you to pause the video, and I want you to try to come up with a conjecture on your own using this data. Now don't try to come up with a really, really challenging one. Just use what you see, knowing that blue whale has blows of 25, 29, 27, 24, and then humpback whales are 8, 7, 8, and 9. So if you can come up with a conjecture on your own, and then we'll go ahead and compare what I have. Alright, so let's take a look at my conjecture. I noticed that when we were looking at the blue whale blows compared to the humpback whale blows, the blue whale blows were always a higher distance than that of the humpback whale. So my conjecture was the height of the blue whale blows are larger than the height of the humpback whale blows. Pretty simple. Didn't have to look into it. I'm not looking for any comparison numerically. Oh, do I divide this by, 3 and add 1, or what is it that I'm trying to do? It was just basic, simple. All you had to do is say, blue whale blows, the height of those are actually larger than the height of the humpback whale blows. So when we talked about the definition of conjecture, I had dropped the word counterexample. So this gives us an opportunity now to talk about what the definition of a counterexample is. Counterexample is just one example that shows the conjecture is not true. Now it comes in a couple different varieties. Either you can draw it out, you can write it out as a sentence, or you can come up with a number. All of these are just proving that our conjecture would not be true. So what I'm going to do is I'm going to go through an example with you. What we want to do is we want to find a counterexample for the following conjecture to prove that it is indeed false. So A, it says 3 points on a plane always form a triangle. I think the easiest way in which I can do this is to come up with a drawing that shows that this isn't always true. So I know that I'm working on a plane, so I'm going to draw out my plane. And what I want to do is I want to come up with how 3 points on this plane don't exactly have to form a triangle. So if I plot 1 point, and then maybe another point, the only way in which this is not going to form a triangle is if the other point sits such that we'd end up forming a line instead of a triangle. So this diagram that we've drawn here is a perfect counterexample to this conjecture, because it gives me that one example that shows that the conjecture is not necessarily true. So why don't you go ahead and try the next two. You can either come up with a drawing, a statement, or a number. I'm probably going to come up with drawings, but you can do what you want. And go ahead and try them on your own. And when you're set and ready, start the video up again. And hopefully we end up having something similar, ideal-wise. So let's take a look at B together. In B, we know that the conjecture says that supplementary angles are adjacent. Supplementary angles are angles whose sum of measures equals 180 degrees. Now they're saying that all supplementary angles have to be adjacent, or adjacent meaning next to each other, sharing a common side. So the one example that I ended up coming up with was I do indeed have two supplementary angles. One of them's 30 degrees and the other one's 150, so when I add them up I get 180 degrees. However, these two angles are not next to each other. They do not share a common side. Therefore, this is a perfect counterexample to our conjecture. Last one. Two complementary angles are not congruent. So if we're talking about complementary angles, we know they have a sum of measures that is equal to 90 degrees, and it is saying they are not congruent. What I came up with is two angles, both of which are 45 degrees, and 45 degrees, since they're both 45, that means they are congruent, and when we add them up, we know that we get 90 degrees, therefore the 45 plus 45 gives me a complementary pair of angles. This is what I ended up having for my counterexample. Could you have stated maybe that the two angles should be 45 degrees instead of drawing them out? Absolutely, and we would take that as a counterexample in a statement form. Either drawing, statement, or the number. Any of those would work. Just pick what you feel comfortable with and what makes sense to you. If you have any questions, let me know in class. Otherwise, have a great night.